Statistical learning refers to a large collection of tools that are used for understanding data. Statistical learning can be divided into two categories, which are called supervised learning and unsupervised learning. Supervised learning refers to a collection of techniques and algorithms that, when given a set of example inputs and example outputs, learn to associate the inputs with the outputs. The outputs usually need to be provided by a supervisor, which could be a human or another algorithm, and this is where the name comes from. Unsupervised learning refers to a collection of techniques and algorithms that are given inputs only and there are no outputs. The goal in unsupervised learning is to learn relationships and structure from such data. In this case study, we will learn the basics of supervised statistical learning. We will look at regression, which refers to problems that have continuous outputs, and we will also look at classification, which refers to problems that have categorical outputs, like 0 or 1, blue or green, and so on. We will mainly use the scikit-learn machine learning library for Python to implement these models. Note that this case study deals with supervised learning only, and we will leave unsupervised learning for the future. In statistics, variables can be either quantitative or qualitative. Quantitative variables take on numerical values, such as income, whereas qualitative variables take on values in a given category, such as male or female. The range of quantitative variables depends on what they measure and what units are used. For example, we might measure annual income in dollars or thousands of dollars. Similarly, qualitative variables can have two or more categories or classes. The male-female example refers to a qualitative variable with two categories, but in principle there can be any number of categories. In some cases, we convert a continuous variable to a categorical variable by specifying the cutoff points between the categories. For example, for income, we might specify that a household with an annual income less than $30,000 a year is a low-income household. A household with an income between $30,000 and $100,000 is a middle-income household, and a household with an annual income exceeding $100,000 a year is a high-income household. Methods in supervised learning are divided into two groups based on whether the output variable, also called the outcome, is quantitative or qualitative. If the outcome is quantitative, we talk about regression problems, whereas if the outcome is qualitative, we talk about classification problems. Note that this division into regression and classification problems is made based on the nature of the output, not the inputs, and it's common for both regression and classification problems to involve a mixture of quantitative and qualitative inputs. In both problems, we have some input variable x and an output variable y, and we seek some function f of x for predicting y given values of the input x. What the best prediction is depends on the so-called loss function, which is a way of quantifying how far our predictions for y for a given value of x are from the true observed values of y. This is the subject of statistical decision theory, which is outside of our scope, but we will state the relevant results here. First, in a regression setting, by far the most common loss function is the so-called squared error loss. And in that case, the best value to predict for a given x is the conditional expectation or conditional average of y given x. So what that means is that what we should predict is the average of all values of y that correspond to a given value of x. Second, in a classification setting, we most often use the so-called 0-1 loss function, and in that case, the best classification for a given x is obtained by classifying an observation to the class with the highest conditional probability given x. In other words, for a given value of x, we compute the probability of each class, and we then assign the observation to the class with the highest probability. Let's look at the foundations of regression and classification on the whiteboard. We're going to start with the regression setting, so I'll just put the R in here. And imagine a situation where we have our random variable x here, which is our predictor, and we have our random variable y here, which is the response. Now, consider a setting where we have a very large number of points. And so our goal is to predict y for a given value of x. The question is, what value of y should we predict? So let's draw a line here. So rather than looking at all values of x, we will look at one specific value of x. I'm going to call the lowercase x. Now, if we had infinitely many points, we would have lots of points here on the line. We would be able to return the mean value of those points. However, it might be the case that we don't have any observations on the line, and then the question is, what should we do? Typically what's done is we look for observations that are close to the value of x. They will not be exactly equal to x, but they will be in the neighborhood of x. And now we can find out the corresponding values of y and try to do averaging over them. Let's then look at the classification setting. In this case, we again have a predictor here, x, and we have an outcome, which is going to be y. In this case, we have a binary response, so we can only have two values. We can either have 0 or 1. So perhaps we have lots of zeros here. We might have lots of 1s over here, and maybe we have a couple of 1s and a couple of zeros over here. Now, for any given value of x, let's say we fix x over here. Again, I'm going to use lowercase for this specific value. What should we return? And the answer is we should try to estimate the probability that y belongs to either 0 class or to the 1 class. So let's write down what is it that we're actually estimating. In this case, we are estimating the regression setting, a conditional expectation of y given a specific value for x. So this is simply saying that this is a conditional mean or conditional average taken over all points that share the value of x. This is your regression function. So if we repeat this for all values of x, we will get a line like this. And typically we might call this f of x. That's our regression function. In a classification setting, we would want to estimate two probabilities. And these are conditional probabilities. So first of them would be the probability that the random variable y is equal to 0 given the value of x. And the second probability is for y equal to 1 given that the random variable, which is the large x, is equal to the small x. And whichever of these two probabilities is largest, that's going to be our prediction for a given value of x.